Okay, question 6. Student investigates moments of forces. So we've got turning moments here, and we know we've got a clockwise moment there and an anti-clockwise moment there. It tells us that the system is in equilibrium. State the relationship between the moment of the weight of the magnet, so the moment of that compared to the moment of the clay. So model answer, at equilibrium, the total clockwise moment, and I should have emphasized that more in lessons, is equal to the total anti-clockwise moment, or the moment of the clay is equal to the turning moment of the magnet. Okay, so now the student fixes a coil, and we can see we've attached it to a power supply. So this is going to induce a magnetic field here. And that's going to, once we turn that on, that's going to pull this down. So the coil of wire connected to a power supply so that there's current in the coil. To bring the system back into equilibrium, the student hangs a 0.05 Newton weight, so hangs this 8.4 centimeters from the pivots. This is kind of clever. If this applies a force on the magnet, we can move the weight forwards and backwards, or side to side, work out the distance, then we can work out that force over there. So we just need to know that the turning moment there equals the turning moment there, and we're going to need our fat, moody dinosaurs. And we know we're going to multiply those two together to get an answer, move that across there, and then divide it by whatever the distance is, and that will tell me the force. And that's the nuts and bolts of this one. Just going to check the units. Newtons, that's fine. That's here. 8.4 centimeters. Well, they're going to cancel out, so I can just leave it as the centimeters because they'll cancel out in the calculation. I'm multiplying it here and dividing it. Whoops, and dividing it here. So we'll remove that unit. So the anti-clockwise moment equals the clockwise moment. So we know 8.4 times 0.05 is 0.42 Newton centimeters. Now we're going to take that and divide it by the 12 centimeters, and we'll get the force is 0.035. Describe how the student could develop the investigation to determine if the size of the force is directly proportional. So that means we're going to have to plot a graph, and we're going to have at least 5 values, and then plot a graph and see if it's a straight line. Okay. So first part then, let's increase the current in regular increments. So I've got an example there, 1, 2, 3, 4, 5 amps. Each time we're going to move the weight to get the system in equilibrium, because as we put a greater current through here, let me get rid of my doodles. As I put a current through here, it's going to be a greater force, and then a greater force, and a greater force, and a greater force. And all we've got to do is start moving you across here, and we'll be able to work out what that force is. So each time, move the 0.05 weight to get the system in equilibrium, measure that distance. Then we can say, calculate the new clockwise moment, so 0.05 times whatever the distance is. If we then divide that by 12, we will get the new force. And then the last part is, now let's plot a graph and see, is it a straight line? So plot a graph and see if there is a linear relationship, and that will prove that it's directly proportional. The student reverses the direction of the current in the coil. Describe how the student can bring the system back into equilibrium without making any changes to the magnet. So let's get rid of all of this. So what it's saying now is, well, before this was pulling down and we had to increase this turning moment to make that pull down. But now this is pushing it up, and this is quite a tricky thing. Well, whatever happens, if I add any weights to this side, it's just going to pull. We're turning it in the same direction, so it's not going to work. So what we've got to do now is move this weight over to that side, and now we can start moving it here to counterbalance it. So onto that there. Move the 0.05 Newton weight to the other side of the pivot, and this will change its direction of turning moment. So that last question is a really tricky one.